Because you know I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, bass. Yeah, it's pretty clear, I ain't no science fool. So you got litmus, well I can turn it blue. Make it go boom boom all over the place. When all the H plus meet all the OHs. Pink phenolphthalein, I think that's straight dope. Mix in a lipid here and it'll make it soap. You want it neutral, pH is low. Better set up a titration with a strong hydroxyl drop. Yeah, my lab tech, she told me don't worry about your eyes. If an acid gets in them, we just have to neutralize. You'll know I love me, my stomach, and all the things it dissolves. But my bile that keeps it from eating my intestine walls. Because you know I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, Ha! I'm gonna do the math to figure out the ratios to react. Stoichiometry, yeah, that's where it's at. And it'll tell you to prepare at least 1 molar for your strong hydroxyl drop. Yeah, my lab tech, she told me don't worry about your eyes.
All right, there we go. Probably not the version you were expecting. But if you want to see this version all about that bass no acid, then you can go and look on YouTube. All right. Coming to somewhere near you soon, I'm sure. All right, so back to physical science and off of the audio. Here we go. We're going to talk about acids and bases primarily, and then we're going to talk about the 4 types of reactions. Now, the first part, acids and bases, are out of your chapter, chapter 21, I believe, right? I don't have that written down, but I think it's chapter 21. Anyhow, so I think that will be accurate for that. But the second half, they talk about oxidation and reduction. That's the 2 types of reactions that they spend a lot of time on. But anyhow, yeah, well, we will. I think it's more useful for us if we'll talk about the 5 actually main types of reactions, because that'll be more useful for what we're covering. The oxidation reduction is probably a little bit more than we need to cover for this. All right. Anyhow, so a couple things. First, I noticed on the last quiz, I think it was, talking about supersaturated. We said supersaturated is when a solution holds more than it can. Well, something's technically that's not possible. But what it is if you heat it up, you dissolve more in it, for example. Then if you let it cool down, a lot of times a lot of that solute that was dissolved stays in solution. So now it has more than it should be able to at the cooler temperature, and it will stay there until something triggers it. And we did a hand warmer thing where we had popped the little metal disc in there, and that set it off, or kind of like caused it to nucleate, so to speak. And when they do rock hard candy, they use like a string or something to give a nucleation site for those crystals to start coming out of the solution. And once you do that, then they start coming out of solution, and it's no longer supersaturated. Eventually, all of it will come out until it's no longer supersaturated. Okay, but anyhow, so that's what supersaturated is. Okay, we say it's more than it can hold, but what we're saying, we get to a temperature where it can hold more, then we cool it down to a temperature, and it has more than it will keep it dissolved or in solution, even at that lower temperature where normally it wouldn't hold that much. Okay, all right, just want to clarify that. So let's talk about acids and bases. We hear a lot about acids, especially in movies. There's always someone spills acid and eats somebody up. There are some where occasionally a body is left in a vat of acid, and if it's the right kind of acid, that's probably possible. They could eat up over time, would decay and eat a lot of the bones up, especially if it's nitric acid. Just for the record, should you ever need to dispose of a body, don't use hydrochloric or something like that. They're strong, but they don't really attack skin much. Nitric acid, which we use a little bit, will leave nice little yellow stains. If you even spill it on your hand, even if you wash it off right away, it will start to attack your skin. Okay, your skin is fairly tough, and most things don't, but nitric acid hates protein, and your skin has a lot of protein in it, so it just goes and eats it up. Okay, so if just for a thing, if you're going to put a body in a vat of acid, get nitric. Okay, anyhow, but in general, acids are not real dangerous substances necessarily. Our stomach acid, yeah, it will burn your throat if you throw it up and burn your nose passages and some other places. Your stomach has a coating to protect it, but tomatoes have acid, milk has acid in it as well as sugar, but it's got lactic acid in it as well. It has citric acid. Anything with an orange flavor to it has acid in it. Aspirin is salicylic acid. So there are lots of different kinds of acids, and we eat them all the time. And that's part of what gives things their flavors that we like, okay? Strong flavors and stuff like that. Bases we use as cleaners all the time. Some of them are dangerous. Bleach, for example, you don't want to drink it, even if you have COVID. It won't help that. It will just kill you. So anyhow, make sure, yeah, they can be dangerous, but most of the time we have lots of acids and bases all the time. Okay, most of our cleaning supplies are bases or acids, one or the other. Okay, so not to be something just, oh, I'm scared of acids or base, and they can be, and if they're strong enough, and we'll talk about that later. But don't just be scared of them just because of that. Now, acids in general tend to have what we call a sour taste, so that's why citric acid, lemons have that. Oranges also have citric acid, but they have more sugar in them, so they taste sweeter, although some people still bother it. You used to be able to buy low acid orange juice, I guess, if you had a sensitive stomach to that kind of thing, got upset stomach really easy and things like that. So there we go. Now, what is an acid? What is a base? Okay. Well, we're going to talk about it in terms of what they give off. Now, when we say something is an acid or a base, just for the record, we're not going to go into it as complicated as this, but we really should say something behaves like an acid or behaves like a base. And usually it's when we put it in water. If we put it in water, it does something. If it's an acid, it does something else if it's a base. Okay. Now, keep in mind, some chemicals could reverse it and go the other direction, and what could be considered acid one time could be a base another. Now, we're not going to get into that, but to a lot of detail. But just keep in mind, technically, it's more accurate to say something behaves like an acid or behaves like a base. But there are chemicals who can reactions go one way, but they can also go back the other direction, and so they could be an acid or a base. Okay, but yeah, moving on. What makes something an acid or a base? Well, basically, we say that an acid is something that releases hydrogen ions or protons into a solution. Okay, so let's look at that in just a second. All right. So when we're talking about acids and bases, first of all, we're talking about what they do when you put them in water. And we know the formula for water is H2O, that's right. But another way to write water is HOH, okay? And in this case, we're thinking one of the hydrogens has like a positive charge, and the OH, which is called, that's right, hydroxyl or hydroxide ion, which has a -1 charge. So it's kind of like you have this positive H hydrogen, and you have this OH, okay? It's same difference, still two hydrogens, one oxygen, just like H2O, just a different way to write it, okay? Or think about it. Now, if you think about hydrogen, hydrogen has one proton, which has a positive charge, and normally if it was neutral it would have one electron circling around it. But if it is positive charge, that means did it fill up another? No, if that would, if we filled up the electron orbital, that would be two negatives, that would give it a -1 charge. No, that's not it. So in order for it to have a positive charge, it has to lose or get rid of its valence electron, and it's just a proton floating around. So we say acids are things that when put in water, release hydrogen ions or protons, okay? Because basically a hydrogen ion is just one proton floating around by itself. Doesn't have the electron anymore. No neutrons, whatever, and it's just a proton floating around. So we also say it gives off protons. Now, for this course, we're just going to say, hey, if something has a hydrogen on it and gives off hydrogens, it's an acid. But anything that gives off a positive proton could be considered an acid, okay? All right, so if you see something that's written like HCl, when you put that in water, a hydrogen comes off. So say here's water with its OHs. The hydrogen gets attracted over here. The Cl gets attracted over here to the negative hydrogens, okay? I mean, positive hydrogen, sorry, positive charges. And so the H and the Cl separate, so we say it gives off hydrogen ions. So it is a acid because it gives off hydrogens when you put it in water, just like salt would separate and go in water. Well, now same thing happens with this acid. Okay. Now, the other thing is that since a hydrogen ion is really just a proton, sometimes we call them proton donors. So when you put them in water, they add a proton. Now, I like to think of it in terms of hydrogen protons floating around, but in reality, a lot of times this hydrogen will join up to water, which is already H2O. Now you get another hydrogen on it, and so you have H3O, but instead of being neutral, now it has a +1 charge. So we can think of this as hydrogen with a +1 charge floating around in water molecules, or we can think of that hydrogen joins up there. Now we have H3O, which is called a hydronium ion. Okay, like I said, it's easier for me to say hydrogen ion, but if you say H3O positive, that's the same thing. They're saying there's an extra hydrogen floating around there that wasn't there before. Okay, so it's an acid. All right, so we said they're proton donors. Now, what is a strong acid or a weak acid? I think this is an important thing I like to spend a little time on, so let me switch back to my other one. All right, so we'll get this come up. Okay, now, when we put an acid in water, we said the hydrogens are released. You have these hydrogens float off, okay? And so we have two acids here, HCl, which is hydrochloric acid, and HCO3, which is carbonate or carbonic acid, very weak acid relatively. Okay, notice when you put the carbonic acid in here, some of the hydrogens come off, but most of them do not. And so this is why it's called a weak acid. We say it doesn't ionize or separate. The hydrogens and the CO3, the positive and negative parts of the atom, do not separate very much. And so it's considered a weak acid. All right. On the other hand, on the hydrochloric acid, you notice that almost every single hydrogen, every single chlorine have separated, and so you've got a lot of hydrogen floating around. So it is considered a strong acid. Okay, why? We're just talking about how many of the hydrogens come off and ionize or separate as a hydrogen ion. All right, if there's not very many, then we would say that is a weak acid. All right, this is a strong acid. Now, it doesn't matter how much water is in it or anything else. If it's a strong acid, it just means all of them come off. Maybe you only add a little bit of hydrogen chloride, so there's only a few of these that come off, but if every single one of the ones that go in there do, it's still considered a strong acid. Okay, all right. Now, I don't want you to get strong and weak acid confused with a concentrated versus a dilute acid. Okay, in these two, we have this, both of these are strong acids. They're hydrochloric acid, and notice in both cases, almost every single hydrogen has come off, so they are strong acids. But if you drop, say, a piece of metal, acids tend to like to react with metals, in here versus here, which one's going to get hit by more hydrogen ions? Well, it's more concentrated. There's the same number of hydrogens in a small area, so it's more likely if you drop the metal in here, it's going to get attacked faster. Here, yeah, some of the hydrogens will attack it, but since they're more spread out or diluted in more water, it's not going to be as strong of a reaction, okay? And it's not going to happen as fast, okay? Concentrated has to do with how much water it is, okay? If there's not much water, then it's going to be concentrated in a small area, so it's going to be, we would say it has a stronger reaction, but that, remember, that's not the same thing as a strong or weak acid, okay? It's more concentrated because there's less water. If you pour water in this, it dilutes it, okay? I can have a thing containing acid. This is HCl, okay? Extremely concentrated. If I took it off, you'd see, or poured it, you would see fumes start coming off of it, okay? Very strong HCl. However, I could drink it, not straight, but say I put it in a pitcher of water or a swimming pool, and then I dip out a cup of water out of it, okay? Then it would have been diluted so much, it would be like the one on the screen here, it's been diluted so much that when I drink some, I'm not actually getting that many, that many acid hydrogen protons, so it would be fairly safe. Still don't recommend you do it, but that's kind of what we're saying here. So we can dilute it, add enough water, and it spreads out the acid enough that it's not going to attack things a lot and stuff like that. All right, and sometimes we say, oh, it's not as strong. But keep in mind, we just say that, but strong acid or weak. But in this case, we're talking about strong acid or weak acid. It doesn't have to do with whether it's concentrated. Both of these are strong acids, okay? And we can go back over here and do the same thing with the weak acid. If we took a weak acid and we took half the water out, then it would be more concentrated, and therefore it would react more strongly with a piece of metal, but it's still a weak acid because not all the hydrogens come off. Okay, and hydrogens, how many of the hydrogens come off vary with every kind of acid. So there's kind of a spectrum from strong acid to weak acid depending on how many of the hydrogens come off. All right, bases on the other hand are of course first, second, and third. Fourth is a home plate and it's not a base. Don't ask me why you have three bases and a different kind of base. Okay, in chemistry, a base is something that when you put it in water gives off OHs. Okay, that's the other part of water. Water has an H and an OH in it. Okay, and so if you put it in water and now it has OHs come off, all right, then it's going to be a base. All right, and so when you put them in water, they release OH or hydroxyl or hydroxide ions into the water. Okay, they also they tend to say it's bitter taste, usually bad tasting. A lot of things that plants are trying to tell us, leave me alone, don't eat me, are strong bases or alkaloids, yellow sap, white sap, milkweed, some of those other things like that that have white and yellow sap, nasty tasting, don't eat them, and people don't. Okay, some of them are actually even poison enough to cause problems. All right, now, since OH is floating around inside a solution, well, they'd like to get back to water, so if you have these OH, negative OHs floating around, they would like to have a hydrogen because then they could join together with it and make water, okay, which is everywhere and everything like that. So they are actually looking for protons. If there's a negative OH floating around, they're looking for protons and they will accept or take in hydrogens, all right? And so they're called proton acceptors, okay, because they will accept hydrogens. They're looking for hydrogens to bring in and make them complete as water. You complete me. You make me water. That's what the base told the acid. Okay. Anyhow, so you get the idea. All right. So, see anything else? One thing that are very slippery. If you ever get bleach or some kind of thing like that on all your cleaning supplies, they feel very slick and slippery. It's also very dangerous in the lab because now you have this slippery, strong base on the floor that corrodes and eats holes in your clothes and stuff. If you get it on it, like bleach would, and now you slip in it and fall out, that's not good. Okay, so you got to be careful with those kind of things. All right, but bases tend to be what we talk about them as corrosive, but they can be, if they're very strong, they can definitely be dangerous as well. Okay, so we hear about acid. Usually, don't hear someone, oh, we fell into some base, you know, but technically, they could also be very bad. But apparently everybody uses acids to really get rid of bodies. Just note, like I said, in case you ever need to get rid of a body, probably better go with an acid. All right, now, to measure how strong an acid or a base is, we have a unit called the pH. Okay, and it's always a little p, even at the first of the sentence, although probably wouldn't make your English teacher very happy if you did that. But technically, it's always a little p and a capital H. We know what capital H stands for. It stands for hydrogens, or if they're added to a water molecule, hydronium ions, but don't have to worry about that, okay? So we're talking about hydrogens, and little p here stands for concentration. So how many hydrogens are in it? If you have lots of hydrogens, guess what? It's going to be an acid, okay? If it doesn't have very many and has more OHs, then it's going to be a base, okay? And so basically that's what the acid, and basically, technically, acidically and basically, that's what has to do with the pH, okay? Now, the pH scale, you may have heard this before, probably from school, runs from, technically we say from 0 to 14, okay? 0 all the way to 14, the middle then would be 7 right there in the middle, okay? And I wrote it off the board so you can't see it, so let's move that a little bit. Okay, so 0 to 14 and 7 is in the middle, all right? Now you say, oh, if we're pH is the concentration of hydrogen ions, then the bigger the number, the more acidic it is. That would make sense, but no, that is not the way it works. Okay, here's the deal. Because pH is the negative log of the concentration. What? Good question. Okay, here we go. In other words, all the log 10 means or log means is what would the exponent on the 10 be to equal this number? All right, so before you panic, let me talk about this. Okay, so if you have something that's 10 to the 7th, that would be 1 with 7 zeros after it. Okay, 10 million just for the record. Okay, now if you have 10 to the negative 7th, that would be 1 over 10 million, and it would be a very, very small number. Okay, so the pH number is equal to the exponent on the 10 that tells you the concentration of the hydrogens, but it's equal to the negative it. So if you have a pH of 7, technically the concentration is 10 to the negative 7, which means 1 out of every 10 million molecules in that solution is a hydrogen ion. Okay, and that is what we call neutral. Okay, in water, you have HOH. If it's pure water, which rarely do you ever find completely pure water, but let's just say it's pure water, then for every hydrogen or hydrogen ion, you have an OH negative or hydroxide. So they completely balance each other out. So we say this is perfectly neutral. Okay, it does not have more hydrogens or more hydroxide. Now, if you add something to the water, if it increases the hydrogens, then it becomes more lower number and has a more acidic. So it gets more acidic as you go this way. Someone said, but the numbers are getting smaller. Well, let's say you go down to 10 to the 6th. Well, remember, it's the negative 6th, so it's 1 over 1, the 6 zeros. So this time, the hydrogens are only 1 in a million. So that's a higher concentration. It's 10 times as strong as this one is. Okay? You get all the way down here, let's just say to 10 to the pH of 1, which is 10 to the negative 1. That means 1 in every 10 molecules is a hydrogen ion. So that is much higher. Okay? And so very, very concentrated. Now, on the other hand, over here, as you get bigger numbers, they become more basic because think if you have a pH of 14, that's 10 to the negative 14, which would be 1 over 1, and yes, you guessed it, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. So 14 zeros after it. I don't know, gazillion, I'm not sure what number it comes out there, but it's a big number, okay, a very small number. So as you go this direction, you get less and less and less. Now, technically, it could get less and less and less and less and less. You could have 1 over 1 with 20 zeros, but in the real life, we don't much get past 14. Okay? Now, on the other hand, as you go down toward this direction, you're getting more and more hydrogens. And technically, because of the way logs work, you can actually go down to a negative 1. We're not going to worry about that. But just for the record, if you ever see that, it is possible to have a negative pH. Okay? But most of the time, we don't. Once again, most of the time we get down to 1 or 0, and that's about as low as we would ever deal with on a regular basis. So we're not going to worry about that, okay? So anything less than 7 is acidic, even though the numbers are getting smaller because it's a negative exponent. It's 1 over 1 with that many zeros. And so the smaller the number of zeros, the more concentrated it is. As you go this way, you get more and more zeros, so it gets less concentrated with hydrogens. Hope that's clear as mud. Watch the other video if I lost you on that, okay? All right. But keep in mind, each time the number changes, since you're changing the exponent, that means it's 10 times stronger or weaker. Okay? A 6 is 10 times stronger than a 7. A 5 is 10 times stronger than a 6. So it's not like, oh, you got to go halfway to 0 to get twice as strong. It goes 10 times as strong from 7 to a 6. And 10 times as strong to go from a 6 to a 5. If you go from a 7 to 5, it doesn't get 20 times as strong. It's 10 times 10. So it's 100 times stronger. So usually when we give pH, we worry about the 7 point something or the 6 point something, because if you go a whole number, that's 10 times stronger. So that's a pretty big jump sometimes. So a lot of times the pH will be done to the 100th place or so, just to show that there's smaller differences like that. All right, because if you move a whole number, it's actually 10 times stronger. 2 numbers is 100 times stronger or weaker, depending which way you're going. All right, so keep that in mind. All right, now, water, like I said, is neutral because it has equal number of H's and OH's. All right, now, remember we said acids like to give away hydrogens and bases like to accept hydrogens. So what happens when we put them together? All right, so what happens when we add them together? Remember, bases like to accept hydrogens and acids, like HCl here, hydrochloric acid, like to give away. So let's just write this out as a formula first of all. We know how to do reactions now. And have HCl plus sodium hydroxide, which is NaOH, basically Drano, very strong base, okay? Now the question is, what's going to happen when we put them together? Well, this one wants to give away its hydrogen. This one, the OH, wants to take the hydrogen. So this H and the OH get together and they make HOH, which we know is homeowners. Oh, no, that's not it. Sorry. Okay, it is water. So first of all, it usually makes water. Not always. There are some exceptions because not every base has an OH in it. Because there are other things that accept protons, and not every acid has an H. But to make it simplify for us, yes, HOH get together and make water. Now, what else does it make? Well, it depends on what the other things are. Okay, in this case, what do we have? We have sodium, which had a positive charge, chlorine that had a negative charge. So guess what? They're going to get together, and you have NaCl. All right, so you get salt plus water. Well, let's try it and see. Here we have an acid, HCl, and a base, NaOCl. How can you tell them apart? Well, technically this one looks so cloudy at the moment, but that's not a good way to do it. You can tell them apart because they have the little labels on them, and hopefully they were done right. Okay, now if I have a very strong acid, this one will eat up metal. Not really good for us either. It's good in our stomachs, but not in other parts of our body. So what am I going to do with that? Well, what about the base? What are they going to do? Well, it's like Drano. So if I mix these together, let's see what happens. Well, first of all, it gets really, really hot. Okay, you can see some little bubbles coming up in there because it got so hot it almost bubbled over. Okay, but if you look at it, you really can't tell a lot of difference about it. It still looks pretty much the same, unless you were holding it, in which case, trust me, it is really hot. So they basically react with each other. Okay, but according to this, what's left over here in my thing? Very hot, but salt water. All right, am I going to drink it? No. Okay, but I could take this dangerous base and this strong acid, mix them together, I end up with salt water. If I did the right concentrations of each, all right, if I did the right concentrations of each, I see, notice I didn't react much anymore, so we probably react with all the sodium hydroxide. All right. If I did it right, it would be salt water, and I could gargle with it, no big deal. But is that good practice? No, it's not. So we're not going to do that. And I didn't measure them precisely enough to do that. Okay, but if we did, we could do that because we have what we call a neutralization reaction. And usually it forms water because the H and the OH gets together to make water, and you get salt. Now, keep in mind, it's not always table salt. This one is. All right, because we have sodium and chlorine. All right, and so when you, what's left over, that's what you end up with. But what if this had been nitric acid, the one that eats up people's skin? Oh, well, instead of sodium chloride, you would have got sodium nitrate, NO3, which is another kind of salt. Okay, so there are. Keep in mind when we say it forms a salt, there are different kinds of a salt, and battery too, for that matter. But that's a different kind of a salt. Okay, but it will form a type of salt, but keep in mind this salt is just a general term of two ionic bonds together, just like sodium chloride, but it could be sodium sulfate, sodium nitrate, could be potassium chloride, potassium nitrate, and so forth. You get the idea. And so it will form some kind of salt and water, and generally the pH is going to be neutral. Once again, is that one completely neutral? Probably not, but it could be. Okay? All right. Now, that's a neutralization reaction. You add an acid and base, and they cancel each other out, basically, and form water and a salt of some sort. Now, just for the record, there are some medicines that have HCl. You'll see hydrochloric acid or hydrochlorine or something like that has been added to this medicine. You think, well, why would you stick an acid on a medicine? Because sometimes it upsets people's stomach because it's got acid in it. But part of it is that when you mix it with water, the hydrogen will stay a part of the medicine, but it'll have a little positive sign to it now. It is polar, has a charge, and it will dissolve better with water. So when you take it and it gets in your stomach, it will dissolve better and be absorbed into your body. So a lot of them will have HCl. If you look at the medicines, they will have HCl or hydrogen chlorine added to it, and that's because it gives it a polar charge, and that means your body will absorb it and dissolve better. Okay. Um, Now, a couple things, and then we'll move on. But let's talk about how do we know the pH? How do we know if it's neutral or not, or if it's acid or base? All right. One of the things people found, there are certain things we call indicators. We use phenolphthalein, the one a while back, when we put it with sodium and it mixed with water, turned pink, purple pink. It turns that color in base. And there are different chemicals. The red color in red cabbage will do the same thing. It will change colors depending if it's a base or an acid. Okay. Now they've done that with paper. And we have what we call litmus paper. Litmus paper is what we call neutral. And if you put a base on it, like this is ammonia, it will turn blue. Okay. On the other hand, if we take something like toilet cleaner and put that on there, it will turn more of a red color, okay? And so this is called neutral litmus paper, okay? And it will just turn red or blue depending on whether you are, which party you're a member of. No, just kidding, okay. No, it's not that kind of litmus test. But people talk about certain issues being a litmus test for political parties. Well, it's the same thing. They're testing them to see if you think like us or you think like them. Okay. Anyhow, you can also have blue litmus paper that if you put acid on it, it will turn pink. If you put a base on it, guess what? It will just stay the same color. Okay. And of course, then that means you can also have red litmus paper. Okay. And red litmus paper is going to stay red if you put an acid on it, but if you put a base on it, it will turn blue. Okay. And so those are handy. That tells us at least if something's an acid or a base. But let's face it, some acids are harmless, and some acids are concentrated enough or strong enough an acid to be dangerous. So how do we know exactly how strong it is? Well, that's why I came up with this. This is pH paper. Okay. They also have little sensors that you can stick into a solution, and it will read out what it is. But these are kind of yellow, although just from getting on my hand, it's already changing color. I'm going to put some, let's do Windex since we haven't done it yet. This is the glass cleaner. Yeah, Windex. Here we go. And if I put Windex on there, it will change color. Okay. And it will turn a very dark bluish purpley. Now, some say, well, but how does that help? Well, instead of just turning slightly, I can compare it to the colors on the side here. And it has a color for every number, 1 through I think this one goes always 1 through 14. Okay, and I can pick out where I think it goes, and it's probably right in there. So it's between 7, 8, around 8. It looks like something like that. Okay, and so pH paper allows you to at least have a specific pH, and so you get a little more definite answer of, is this dangerous? Is it safe? Is it whatever? Okay, if we do the toilet bowl cleaner, on the other hand, it's going to be an acid. Now, remember we said most cleaning supplies are bases, not acids. Why can a toilet bowl cleaner be? Well, think about it. We said acids don't like metals. They also don't like limestone and some marble and things that people have in their sink sometimes. But if you're a toilet bowl cleaner, you're going to be around porcelain. You're not going to be touching any metals, so they can actually use acids. So acids would be good cleaners. It's just that too often the time they would attack good stuff. Okay, and if we put that one up there, it's going to be kind of a reddish color in there. And it's going to be about a 1 or a 2, so it's very strong acid. Toilet bowl cleaner is. In fact, you can take toilet bowl cleaner, squirt some in a little container, put some aluminum foil, and guess what? Metal doesn't. Acid don't like metals. It will get to it. Get down to business in a hurry. Okay, fun stuff, but be careful. All right. Okay. So basically, that's what we're talking about pH, and that's how we would measure the pH. Either a litmus paper to tell if it's acid or base, or more specifically, something like pH paper or a meter that actually reads off a specific number to it, which of course would be the most accurate way. Okay. Now, listen, there was something I was going to cover. Did I miss that? Okay. No, I think that's it. Okay. So let's think about buffers. Okay, in our bodies, for example, we can't have the pH just constantly changing. Your blood is a pH between, a little rusty, I haven't done anatomy for a while, but about from 7.2 to about 7.45, I think. It's slightly basic, but if it gets much either side, you get acidosis or alkalinosis on the other side, and basically you start dying. Okay, so you need to keep it about the same. And so your body has what are called buffers. In fact, bufferin is something they put on aspirin because aspirin's an acid. They put this buffer around it so that when you took bufferin or aspirin, it didn't give you acids, upset stomach. It would buffer it and keep the pH of your stomach from going up. Buffers are things that keep the pH from changing rapidly. Okay, and just to give an example, say you have sodium carbonate, which is more or less a base. Okay, and if there are extra hydrogens floating around in your system and it's becoming too acidic because you're getting higher concentration of hydrogens, sodium carbonate can pick those up and become sodium bicarbonate. Don't ask me why there's a hydrogen in there. They call it bi, but that's just one of those weird rules that don't fit the rules of naming we talked about. Okay, so basically, if your blood gets too acidic, too many hydrogens, the sodium carbonate will pick that up and make baking soda basically in your blood that will lower, or will actually raise the pH, make it less acidic. Okay, now on the other hand, what if that happens? Your blood gets too basic. Well, the sodium bicarbonates can let go of the hydrogens, lowering your pH, making it more acidic, and reducing the pH so it's not as basic. Okay, so it can just kind of pick up hydrogens if it needs to, or then this one can let them back out if you need your blood to be more acidic. And they buffer your blood and keep it from getting too acidic or too basic and kind of keep it under control. Okay, and it has to do also with carbon dioxide that you breathe in and some other, which you can say carbon dioxide obviously is necessary to make the carbonate and so forth. But it's very important to keep it from changing too drastically. Okay, a lot of times you don't want that. If you're doing a reaction, making chemicals, sometimes you have to keep the pH constant. So you need some kind of buffer that keeps it from doing that. Okay, now the next thing we're going to talk about is titration. All right, and it goes back to, we were talking about litmus paper and stuff. It's a way to measure the pH, but we'll talk about that. It doesn't give you an exact number, but it is very good for comparing two things and seeing which one has the higher pH. All right, we'll be back in just a sec. All right, we're going to have this cleaner. This is a ammonia-based cleaner, so it's a base, looks like most cleaners are. Okay, we're going to add some phenolphthalein, which took almost, went around the whole bottle and almost ran out of room, trying to get the whole name on there. But remember, that's our indicator. And when we get a base, like the sodium hydroxide that formed when we put the sodium in it, it will turn purple. All right, I'm going to push it with my thumb. If you were doing this lab, I probably wouldn't let you do that. I would give you a stopper, but I mislaid my stopper, so we'll be all right. Good stuff. Okay, so it is pink. Now, it's not a very strong pink. It's not a very strong base, but it is there. Now, I'm going to add some vinegar to it, which is an acid. And what's an acid going to do to a base? Neutralize it, right? But if I measure how many drops it takes, that tells me something about how strong it is. So let's put 1, 2, 3, 4, 5. Now we're going to shake it. Well, actually invert it. Okay. 5. It's still pretty dark. So 1, 2, 3, 4, 5. Ooh, maybe 6. Okay. But, you get the idea. All right. And it's getting a little lighter. I think I can go with 10 this time. So I got 10. So 10 more makes 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oops. Maybe gone over a little bit. Okay. 22, we'll say. All right, and it's still there. So let's do 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, maybe 11. Okay, boom. There we go. Still pretty. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And it's getting there, but still about 50. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so we did a little more. And it's still had done it, but it's getting lighter. All right. All right. We're up to about 70, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. It's getting lighter. Still not there. Okay. Now I'm going to speed things up just a little bit here. Now we can start seeing it's starting to clear up. And if I shake it, boom, it's pretty much cleared. To do it, you'd have to hold it up to something white and make sure it looks, but it looks pretty clear. Okay, so it took about 80 to 90 drops. Okay, and that would tell us how much of the base it is. Now, if I take another cleaner that we do have another one here somewhere. All right. This one is the Amazing Suds. All right. All right. And I'm going to pour some of it in there, and let's see how much it takes. Now, I could count the number of drops. First of all, I got to put some phenolphthalein in there. It's a little bit pink already because I didn't clean it out really good. And so it still has a little bit in there. But I'll put some more in there. All right. Now, first of all, it's about dark, but it looks similar to what the other one did. All right. Now, this one, we'll see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know it's going to take a little longer. So once we know it's pretty safely dark, we can keep trying. 10. 10. All right, about 40. About 60. And it's still pretty dark. 80. All right, and so on. And this one, I can tell just by the color of it, we got a ways to go yet. Okay, it's still not, it's almost 100, just like the other one. Now, to speed things up, I'm going to use some of that hydrochloric acid that was very, very strong. Okay. And boom, just like that, it cleared up pretty quick. Okay, now, you see how clear it is. I'm mixing it. I'm mixing it. I don't need my fingers. That's still pretty strong stuff in there. But we can tell the second one was probably going to take close to 200 drops. We didn't have time to do the whole lab for you, which we would have if you'd been here in person. But that's basically how you would tell. It doesn't really tell us. Technically, you could do formulas, and if you knew how concentrated the acid was and the base that like we were putting vinegar acid in there, we could calculate and figure out exactly how strong it was. But it's a good way to compare. If you have two things, you don't know which one's stronger, you can compare them by how many drops it takes. Now, you can have a base that you add acid to, which is what we did here, or you could do it the other way around. If you had 7-Up or Sprite, you could add the phenolphthalein to it, and it would stay clear, and you keep adding drops of a base until it finally turns purple and stays purple after you shake it. So it's the same way. You can either add a base to an acid to see how strong it is, or you can add a base to an acid to a base. And either way, whichever one takes more of the acid to neutralize it is going to be your stronger one. All right? All right, so that's titration. And titration is where you measure how strong an acid or base is by adding the opposite one until it neutralizes it. Now, when you add acids together, you get salts. Okay, and salts are electrolytes, which means they can conduct electricity. And in our body, that's very important. Talk about electrolytes in Gatorade. It just means there are salts in it. And they dissociate or separate in water. And there's some more stuff about salts in the other video, but we'll let you read that. Also, social applications about acid rain and things like that. But I will let you also watch the other video for that. We don't want to spend that time right now. Now, let's talk about type of reactions, okay? And we're basically going to talk about 5 main types. And so I want to discuss those for a little bit, and then we will move on, okay? All right, here we go. We're going to do some reactions, and we're going to use some fire. That's always good. All right, so we have a torch. All right, now for my first one, we are going to take, this is steel wool. Okay, everybody's seen steel wool. Maybe you have to use it to scrub or sand things a little bit. Okay. All right. Now, if I stick this in the flame, whoa, you will see all kinds of stuff happening there, right? Very exciting there. All right. I'm going near my finger, so I'm going to let go of it. All right. Now, back in, it'll still do some, but most of it's been done. Now, interesting enough, you say, well, how do you burn steel wool? Okay. Why does it keep burning? Okay. Basically, this is a reaction, and it's reacting with oxygen in the air. And compared to what it was like before, now it's very brittle. Okay, a lot of it comes off in my hand and breaks a lot. I don't know if you can see that or not, but breaks off, kind of like rust, basically, kind of like it rusted it. Okay, and what it did, it made, instead of iron, now it's iron oxide, which is kind of like rusted, and it basically rusted it, turns it a darker color. It's not the same color it was before. Okay, but basically that's what's happening there. So you're actually adding oxygen to it. So now instead of iron, it's iron oxide. Okay. Another example would be, this is magnesium ribbon. This is kind of a silvery gray ribbon. It's pure magnesium. All right. Let me get my tongs real quick, and we will do this. All right. So we're going to take our magnesium ribbon, put it in here, and it's going to react. It's also going to be very, very bright. If you were here, I'd say don't look at it, but since you're not, you don't have to worry about that. Okay, now you can see it's white powdery. And if we had taken the weight of it before and after, I'm very careful because some of it sticks to the end of my tongs here, you would find that it actually weighs more than it did when it was just the magnesium metal, even though now it's white, very crumbly stuff. Okay, it has formed magnesium oxide. Okay, and so once again, it is taking magnesium plus oxygen in the air and has combined it into a new thing. All right, so that is the first type of reaction. When you have 2 or more reactants and you put them together to make one one product, then that is a synthesis. Synthesis means to put together. So you're putting 2 or more things, 2 or more reactants, and you end up with one product. Okay, so that's that one. Now, let's talk about some of the others. All right. Next one I'm going to do is, I believe, decomposition. Decomposition. If something breaks down, like decomposes, what does that mean? Well, it means it's breaking apart, right? And that's basically what it means in this case, chemically as well. All right. It's going to mean that something is breaking apart. All right. So in this case, we're going to do something that we've talked about already before. But we're going to get some liver and some hydrogen peroxide. All right, so if you remember last week, we have some liver here in the end, nice slimy liver, and we have hydrogen peroxide. Remember, hydrogen peroxide, H2O2, and over time, oxygen breaks off, bubbles off, very slowly normally, but if we add, let me get a different test tube. All right, and we'll pour it in there. I typically not do it slowly because it may take a while to get a big mess all over me. So we'll just do it like this. All right, I'm going to pour some hydrogen peroxide. You can see that you don't see anything happening. It is happening, but very, very slowly. All right. But if we add it to the liver, you can see it now bubbling merrily along. The liver's kind of cold, or probably even be doing more than that, but you can see that. Definitely speed it up because the enzymes, remember enzymes, which are catalysts that live inside living things, okay? And so they are bubbling merrily along there and continuing to rise up the test tube, okay? That is a decomposition. We're breaking one chemical, H2O2, into water, H2O plus O2, or oxygen bubbles. And so because of that, it is decomposition. We're taking one reactant, breaking it down into two or more products. In this case, two products, but it could be more just depending on your reaction. All right? And that is decomposition because you're breaking one reactant down into more than one product. All right. Now, the next one we're talking about, we have some either replacements or they're called displacement. Some of you hear it called replacement. Some of you hear it displacement, but whatever. Okay. All right. So let's do one here first of all. We have, this is copper. You can see, I believe, all the little strands of copper in there. Okay. And we're going to add silver nitrate to it. Grab that. Silver nitrate is in here. It is actually contains silver, so it's fairly expensive. We don't use a lot of it, okay? Because of that, sometimes we try to not overuse it. All right, and as you notice, there's a lot of black stuff on it. That's because when it reacts with water, it reacts with it, it pulls the silver out of the solution and makes silver tarnish or silver oxide, and we don't like that because that messes up the stuff we're trying to use for our reaction. All right, so silver nitrate has to be, and that's why it's in this colored bottle. All right, so that the light will not react with it and cause it to do that. All right, now we're going to leave that for a little bit. So basically, what's going to happen? The formula for silver is AgNO3, right? Silver, AgNO3 is nitrate, but turns out that copper has a stronger attraction to the nitrate than the silver does. And so what happens is, you will notice, and we'll probably look at it again later, but you can see it's already getting kind of fuzzy looking at the bottom, and all that, and that's actually silver that's coming out of the solution. And you may even tell a little bit that the solution starts feeling a little bluish because that's what copper does. And so copper is switching places with the silver, and instead of silver nitrate, it's becoming copper nitrate, and you're getting pure silver hanging off of that. Now, if one even tries to come and get this and say, oh, I can get rich on it or anything, trust me, there's not as much silver as it looks, although that is actual real silver right there, pure silver coming out of the solution. Okay, very expensive stuff just because it has that, so we try not to overdo it, but there you go. All right, so that is it's kind of like when the silver nitrate is silver and the nitrate, they're going together. They're like a couple going to a dance, and someone else at the dance cuts in on the silver, so in this case copper, I'll take your place. And so that's kind of a single replacement because the silver is taking the copper's place. Okay, so one element is replacing another element that's in the compound. All right, so it's kind of when someone cuts in on a couple and breaks up the couple. All right, but that brings us to double replacement. Okay, now we're still going to use our silver nitrate, but we're going to have to get some other chemicals, so I'll be right back. All right, for our next one, which is going to be double replacement or double displacement, depending on what you prefer to call it. All right, and in this case, instead of a single element like copper being added and taking the place of the silver, now we're going to add two compounds. The first one is the salt water, which is in there, NaCl, salt solution. So we're going to dissolve salt in water. Okay, but that's sodium chloride. That would be NaCl in parentheses AQ, because it's dissolved in water, plus we're going to use our silver nitrate again. All right, so good old silver nitrate, and silver nitrate is AgNO3. Okay, and we are going to add them together. All right, let's see what happens. Whoa, look at that. All right, so we have kind of milky stuff forming in there. All right, just for the record, that's called a precipitate. Just like when liquid formed out of the air, so you have gas or air, or some liquid forms and begins to fall out of it. That is called a precipitate. Well, if you have a solid appearing in the middle of a liquid and beginning to fall, you can see at the bottom, it's falling toward the bottom, just like a snow globe there, sort of, okay? Then that's also called a precipitate. All right, you have another phase, a solid in this case, because what happens is you have silver nitrate, which is like one couple, silver nitrate, and you have sodium chlorine. All right, and it's kind of like this time you have two pairs that went to a dance, and they decided, hey, I would rather swap partners. Okay, it's weird, I guess, something like that. But anyhow, I wouldn't know. Anyhow, but it switched partners. So now instead of sodium chloride, you have silver chloride. That is what the white stuff is, and the white stuff does not dissolve. It's not soluble in water, so that's why it formed a solid. When it forms silver chloride, it comes out. Now the sodium pairs up with the nitrate, and you have sodium nitrate. So once it settles out and all the white stuff's at the bottom, the rest of the solution up here will be sodium nitrate, which does dissolve in water, and so it stays there. But very brief, kind of a snow globe, like I said. Very nice. Okay, so basically that is a double, because now the sodium and the silver have switched partners, and like I said, it's kind of like a double date where people go home with the other person's date. I don't sure I recommend that. It's a good way to lose friends, probably, but anyhow, that's kind of what it's like. All right, let's do one more example of that, and then we will move on. All right, so first of all, we start off with sodium hydroxide, which we used our neutralization reaction a minute ago. All right, and we're going to add it to copper sulfate. Now, copper sulfate, copper compounds tend to be bluish or green, and so it's kind of very pretty copper. Okay, both liquids, very clear, as you can see. All right, we're going to pour the copper sulfate in there, and let's see what happens. All right, and you can see it's forming a very solid jelly type precipitate in there, very kind of, I would say, green. If it were me, that would be my guess. All right, and so once again we have switching partners. Okay, the copper sulfate and the sodium hydroxide, the copper and the sodium have traded partners. So instead of sodium hydroxide, now we have copper hydroxide. That's what this contested party here is. Okay, and instead of copper sulfate, we end up with sodium sulfate, which is just a clear liquidy and would be mixed in with that. Okay, so that's just another example where they both switched partners. All right, now just for reference, let's look back. We have this is our single one that we put the copper, you can still see the copper up there, but you can see it has really grown a lot of crystally silver. That's a single replacement where it's taking its place. Just for the record, I did not do this earlier, but you could take a nail, let me find my nails real quick here, and stick the nail in the copper sulfate. Well, the copper is steel, which is roughly iron. Okay, plus something else, but we'll just say iron for our sakes, since we can't find pure iron nails. All right, now if I were to drop this nail into the copper sulfate, the same kind of thing will happen. The iron and the copper will trade places, and they will end up being a sheen of a coat of copper. We'll have a copper coated nail, but we'll check on that here in a minute. But once again, that would be a single replacement. All right, now that brings us to our last one, which is combustion. Okay, combustion is pretty simple. We did an example of it already, really. When we lit our torch up here, we have either propane, we have natural gas, we have methane, but this is propane. We have propane fuel coming out, and it is reacting with oxygen. Anytime something combusts, it's combining with oxygen. You have to have oxygen in order to burn it. And then it produces water vapor and uh, carbon monoxide sometimes, and dioxide and things like that. Combustion, always the things burn, but also it always involves oxygen. You have to have oxygen to burn things. Okay? And so the last thing we're going to do then is to look at the burnings and how it uses oxygen, and then we'll move on. All right, so here we go. We're back. We have a candle. How exciting! A little tea light candle, and I'm going to see if I can strike an old-fashioned book of matches. You don't see those as much nowadays as you used to, I don't think. But anyhow, this one's burning pretty good. That's good. All right, and we have the candle. Now, as long as I leave the candle like that, it's going to keep burning. But we know if I stick this over it, eventually what's going to happen to it? It'll take a while, but eventually it's getting fainter and fainter, and eventually it dies. Why? Because it is a reaction. Combustion requires oxygen. Once it's used up all the oxygen in the container, then it can't do anymore, and so it stops. Now we're going to try to do this in hopefully a little bit more dramatic way. All right, we have just some water here, and we have a match. We have a candle that I'm going to try to light in there. We'll see if I can do this. Reach down in there and get it lit before it burns up the match, but we'll see. Barely. Ouch. It almost got my thing. All right, but there we go. Now, if I take a graduated cylinder and stick it over that, it burns out pretty quickly. Why? Because there's not much oxygen in there. But I don't know if you can see this. I think you can. In there, almost to the top of the candle. Actually, what put it out is the water rose up. Why did the water rise? Because it was burning up oxygen. It used up the oxygen. Something had to take the oxygen's place, and so it came in and sucked it up. Okay? And so sometimes you suck it up. Now you know that, yes, if you can do it because the candle can do it, right? Right. Okay. Anyhow, bad joke. All right, moving on. Last thing I want to do is a couple things that we're going to do before we leave, because they produce dangerous fumes, and I don't want to be sitting here breathing them for a long time, so we'll just do that. All right, so we're going to do a couple of experiments here. We said early on that acids, generally speaking, do not like metal. All right, so let's demonstrate exactly what that means. All right, so we have 2 spoons here. Okay, here's one. I'll put HCl in that one. Hydrochloric acid. All right. Let me find hydrochloric acid real quick first of all. Hydrochloric acid. Oh, there it is, right in front of me. Okay, so we got to do that. Let me get some hydrochloric acid. Be careful not to breathe any fumes, because it does fume off. Hydrochloric acid, HCl, is technically and you may be able to see some of the fumes coming off there. I don't know. Can't tell now. But basically, it is a gas dissolved in a liquid. So if it sits around, a lot of the gases will collect, and if they leak out the lid, if you don't have the lids on tight, they will eat up anything that's metal in the room. And a lot of times, if you go into a lab room or in a storeroom and you see all the metal things with rusty falling apart, it's probably because they did not have good seals on their hydrochloric acid. Very difficult to keep it in there and really sealed good. All right, now we're going to take some zinc. This is just silver metal, zinc, like what's in our pennies. And we're going to drop a couple in there and see what happens. And as you can see, it worked very quickly. Now, just for the record, you have HCl. We put zinc in there. The zinc and the hydrogen are changing places, and what's coming off is hydrogen gas. Okay. Push it up. We have used this before. Sometimes when we do explosions, we like to do. This is a good way to get hydrogen gas that you can use to cause akin to oxygen, in that they're both explosive gases. Okay, so if we trap the gas, we can actually use it to blow up or cause an explosion. So, but we're not going to light this one. Now, once again, though, probably some of those fumes are also hydrochloric acid, and that's why we are not getting up real close to it, because we do not want to breathe those. Now, another thing is nitric acid. If you remember, nitric acid, we said, is the one that gets, if it gets on your fingers, it will attack your skin just because it does not like proteins, and we are made mostly out of protein, or a large part of our bodies are made out of protein. So it can do a lot of damage to body tissue, and in test, we said that you could, of course, use it to get rid of a body, but obviously we didn't really want you to do that. Okay, now we're going to use this one. And this is nitric acid. Now, a famous chemist once had an experience with nitric acid, and he said he had read that nitric acid acts on metal, so he had poured some on metal. Well, it also got on his hand. He realized that it also acts on his hand, and a very painful experience, but he said it turned him on to chemistry. So I'm not recommending that's what you do, but we're going to put a copper coin in here just to see, does it in fact react with that? All right. Now, notice not as instantaneous, definitely, as the hydrochloric acid. In fact, rather disappointing at first, but it's getting its speed up. Okay, it takes a little while. All right, you can see now it's starting to bubble some, but not a whole lot. All right. Now, one of the problems with this one, and why we do it with a lot of ventilation, and we're all looking down in it, and when it gets going good, is because adding the coin there may speed up a little bit. Basically, it's going to give off a brownish gas. That gas has dangerous nitrous oxide gases, not the kind that makes you laugh and giggle, but this one is actually kind of deadly. So we're going to try to stay back away from that. But to be honest, it's not acting as though it's very, starting to get some bigger bubbles coming up, but still hasn't really got it going good. And part of it may be the corrosion on the outside of it. It's causing it, having a little trouble getting around it to actually get to the copper. But it is starting to. And I don't know if you can tell, but there's starting to be a difference in the color. Instead of being clear like it was originally, it's starting to turn a little bit of a bluish color. And remember, blue is an evidence of copper solution. So the copper is being reacted with, and so we're ending up with copper nitrate instead of my brain just went dead. Copper nitrate instead of nitric acid. The nitrate part, HNO3, the nitrate part is combining with the copper to make copper nitrate. All right, and among other things, it will also give us some hydrogen gas, but it also gives some nitrous oxide gases. I don't know if you can kind of tell, it's starting to get a little brown around the top, so you can see that brownish color. That's the gas we're talking about, but so far it has not really got kicked into gear yet, but it is getting there. All right, and so anyhow, these are also some single replacement reactants, as well as just showing how acids do not really like metals and are very reactive with it. Okay, you can kind of see the brown is still again in there, but and getting blue at the bottom, but kind of a disappointing nitric acid. Sorry, usually it kind of billows out nice and smoke, and I have to go leave off over here and let it kind of clear out before I come back in the room. But we usually go outside and do it, or underneath a fume hood. So, anyhow, that's it. Don't forget that you have your quiz. I mean, turn in your questions, and then next week will be your quiz. All right. Good news is no test yet, but that's still a week or two off. Okay. I guess after next week. So enjoy this week before the test. Have a great day.